So now I just have
Oh
to...
yeah, I forgot to mention, we are actually recording the talks unless you don't want them to be recorded.
I don't want mine recorded.
Okay, I make a note of that. Please, Kevin.
So first I'd like to thank the organizers for inviting me here to share some of my work. It's a great opportunity and I love the conversations I have at the INT. So this is work I'm doing in collaboration with Chris Green and Javier Fonseca. In particular, I'm thankful very much for Javier because he actually provided me the correlated Gaussian code to get me started in this direction. And then Chris, with his numerous suggestions on how to proceed, is always very helpful. I realized actually after I submitted the title of my talk, I probably should have done it in the reverse order because I'm first actually going to talk about what we've done in developing the hyperspherical approach. And then I'm going to show the applications of the few body systems. So just to get us all on the same page, I'm going to start by talking about how we divide up and conquer the Hamiltonian using our hyperspherical picture. And then this is kind of a joke to me because there was a Review of Modern Physics article that was put out last year, and actually Dirt is one of the co-authors, in which everything that Javier had done we called correlated Gaussian hyperspherical technique. And in the review article it's called hyperspherical explicitly correlated Gaussians, but it's all the same. And I probably should stick with what's in the review article if I want to be more modern. And in particular, what I'm interested in sharing today is what we've done to improve the technique in terms of improving and speeding up the matrix element calculations, because in the end it's just a basis set method. And then again, I'm going to finish up by talking about the Coulomb systems that I've been studying. So to start, what I'm going to do is just look at a Hamiltonian, a few-body Hamiltonian. And in this cases that I'm interested in, we can always separate off the center of mass. And so I'm going to focus on the relative Hamiltonian where I have n Jacobi vectors, each of them represented in d dimensions. And so I'm just going to have my relative Hamiltonian, which breaks up into the kinetic and interaction potential, and in a way Cartesian coordinates, that first line. But I'm going to recast everything in terms of hyperspherical coordinates. And what's interesting about doing this is that we end up with a single length, the hyperradius, and everything else is given as a hyperangle, where the Jacobi coordinates, the vectors, describe two of the angles, the polar and azimuthal, and then the ratios of the lengths of the vectors give us all the other defined hyperangles. So what I have written here is just the hyperradial kinetic energy, which if I went to a single coordinate, a single Jacobi vector in three dimensions, we would just get back to the usual three-dimensional radial part of the Hamiltonian. And what I haven't shown here is the angular part, because what I'll actually show is that the angular part's not needed. So the angular kinetic energy, the hyperangular. And how we approach this in our divide and conquer is we write the solutions as a product of radial functions and the so-called channel functions, which are parameterized by the hyperradius. And only in the non-interacting limit, or I guess in the case of zero-range interactions at unitarity, this is shown to be exactly separable. But in general, we always have this parameterization in R. The prefactor in terms of R is just to reduce the resulting equations into one-dimensional equations in the end. So what's nice about this particular choice of semi-separability is that the channel functions are orthogonal for every fixed hyperradius when we integrate over the hyperangles. And the other thing that's nice about them is they solve the adiabatic Hamiltonian, which I'll show later, in which for every hyperradius, we can actually get a set of hyperradial potential curves in our adiabatic parameter, R. So in plugging in the assumed semi-separable solution, what we end up with are a set of one-dimensional equations that are all coupled here because of the imperfect separability we have in the hyperradius and hyperangles. So you see here, the coupling terms, which we call the P and Q matrices, are just because we have the partial derivatives with respect to the adiabatic parameter that's still left over in the angular parts. What's nice about doing this is oftentimes we can actually get away with ignoring the couplings if the potential curves are well separated. And we can actually use this as a single channel approximation to actually pull out some physics. But in general, what we get, the potential curves already give us a nice physical interpretation of what's happening in this adiabatic parameter. So what I'm actually going to focus on is solving the adiabatic Hamiltonian. So this is what's left over after separating into the radial and channel functions. And the channel functions are the solutions to the adiabatic Hamiltonian. So the first term here just comes from the scaling in R that we did. This is the hyperradial kinetic energy. And then we have our interactions rewritten in terms of the hyperspherical coordinates. So as I mentioned before, if we don't have interactions, it's exactly separable. But in our case, we are having interactions. And so let's just choose a basis to attack this problem. The basis we're going to choose are the explicitly correlated Gaussians. And you might ask, why Gaussians? In particular, they're very flexible. And you can actually talk to any physical chemist. I mean, they develop packages around Gaussians because most of the times the matrix elements are analytically solvable. The Gaussians that I'm going to show here, just for simplicity, I'm going to use what I call, or what have been called, spherical Gaussians because they describe states with total angular momentum 0 and positive parity. And having separated off the center of mass, each basis function is given as just the Gaussian with variational parameters alpha, and it's just the magnitude of the difference between the different vectors, the position vectors. And so what we see is we'll end up having, for every basis function, n times n minus 1 over 2 variational parameters. But rewriting everything in terms of our Jacobi coordinates, we can write it in terms of a matrix equation where we have A as the correlation matrix, which is just a function of the different variational parameters. And this is where the traditional and hyperspherical approaches kind of diverge from each other. Because in the traditional correlated Gaussian approach, we would just stick with Cartesian coordinates and work from there. In the hyperspherical picture, what I want to do is rewrite the basis functions in terms of hyperspherical coordinates, in which I have my single length scale and then some function, which is pretty ugly, of the hyperangles. And what I want to do is fix the hyperradius and integrate over all these hyperangles. Oh yeah, and if you want more details, the review article is very nice. So, first I want to go over what has traditionally been done, like starting with Javier's work. And the main idea is that we can always switch to a basis that diagonalizes the sum of the correlation matrices of the two basis functions. All the examples I'm going to show is just the overlap matrix because I don't want to lose anybody in terms of some of these details. But once we've done this, we basically get a Gaussian that the argument of the Gaussian is much more simplified. And we can actually integrate analytically over all of the polar and azimuthal angles of the Jacobi coordinates. So that's what I have shown here. In doing that, we get some prefactor that depends on the volume element of the integrals we've done. And then what we're left with is Gaussians of a mess of sines and cosines. And I write this in, this is how I view it now, given what I've done to improve the technique. But I don't want to downplay what's been done. But in general, this was a mess because once we actually have done the first two steps, we can only do one more integration analytically, at least easily, and we get Bessel functions and a whole mess. And then what we're left with is n minus 2 numerical integrations. So for a few body system, it's not so bad because computing power is always increasing, and doing numerical integrations at the 4-body level, so 4 bodies, 3 relative Jacobi vectors, we would only have one numerical integration for the 4-body system. So that's not so bad. But if we want to scale this, we're going to keep running into more and more numerical integrations. And as I said, I don't want to downplay what's already been done. So at the four-body level, what I'm showing here is some work that Javier did, in which he looked at the zero-range interacting, or the contact interacting system of four particles, so 2 spin-down fermions and 2 spin-up fermions, using a Gaussian interaction, which is very simple to implement because it's just modifying basically the overlap matrix elements. And what was neat to come out of this is to see when we plot the potential curves in units of the binding energy of the universal dimers, what we see is the ground state when we go to zero range, which is shown on the right. We can actually get out, or we see that we have dimer-dimer states, and then we have atom plus dimer states, and then we have, at this threshold, a set of curves that go to the full dissociation limit. Or plotting this in a different way at unitarity, what you can see as you go to the zero range limit, you can actually extract the different universal coefficients. So I don't want to dwell on this. I'm just basically giving props to what's already been done using older matrix element techniques where numerical integration is needed. So now we're going to do a homework problem together in which shows how we do the integrations for the matrix elements. So we start with two basis functions, two spherical Gaussians, zero angular momentum, in the hyperspherical coordinates, in which we fixed the hyperradius at some constant, which I call R0. And we just bring the two functions together because they're Gaussian, so you can do some easy things. But now here's our first trick. So what we do is before, where we had something that's a constant, by introducing an auxiliary integration over a delta function, we can rewrite it as a variable. So not so bad. And then moving on, we can multiply by different scaling factors of the hyperradius. And I can get away with pulling out the constant because of the delta function. But in the end, what it allows me to do is rewrite the volume portion, the volume element. If you're familiar with hyperspherical coordinates, you see that this is the full volume element in those coordinates. So at this point, we can make a coordinate transformation back to Cartesian coordinates. Now, why this is a key step is that it's already known that most matrix elements of this basis set expansion are known analytically. So if we can do things in Cartesian coordinates, we can probably just go to a lookup table and pull out what matrix elements we need. But the downside is we still have this delta function to deal with inside the integrand. So that's where the next trick comes in. We can rewrite the delta function in terms of a Fourier transform. And in doing this, it allows us to apply the further tricks that are used in the Cartesian coordinate system. In particular, we switch to the basis that diagonalizes the sum of correlation matrices. So D here is the diagonal form of that matrix. And Y is going to a unitary transformation from X to Y. And so what we see is all we've actually done is now we have an auxiliary integral over omega, which is the conjugate variable to the hyperradius, the square of the hyperradius. And we've shifted all of our eigenvalues into the complex plane. But because everything is very nicely separated in terms of an integral over the full Cartesian coordinates, we can actually perform that integral, and now we're left with a one-dimensional integral that we could do numerically and hopefully analytically. So this was the big step in this development, because this is for any number of particles in any number of dimensions. So we've actually reduced the complexity of the hyperspherical method to put it almost on equal footing with the traditional correlated Gaussian approach. But we're not done. We have some final tricks that we can look at. So as I mentioned, we've shifted the eigenvalues of the matrix just into the complex plane. But if you notice, if D is even, then these are just simple poles that lie along the positive imaginary axis. So we can just apply our usual contour integration techniques and we're done. But in our case, we want to see what happens when the number of dimensions is not even. And in that case, we can apply convolution theorem. So just to remind everyone about the convolution theorem, how I think of it is if the integrand is separable into a product of two functions, then the Fourier transform of that product is equal to the convolution of their individual Fourier transforms. It just so happens if n equals 1, we know what the Fourier transform is of a single one of these factors. So now we just have to convolve functions of this form. And again, if k is 1, that's equivalent to 2 dimensions, so we just have convolutions of Gaussians in 2 dimensions, which are just more Gaussian, so that's pretty easy. But what if we have to do more complicated? Then we have to perform the full convolution, and just to remind you what that is, this would be from minus infinity to infinity, but the functional forms are restricted because the hyperradius can only take on positive values, so it basically cuts the limits of integration from 0 to t, where t is the square of the hyperradius. So let's do that a couple of times. And since I'm a few body guy, I like to start at the ground level and work my way up. So if n equals 1, nothing new. This is just a nice confirmation that we get back what's already known, because up to n equals 2, everything is analytical, at least from previous brute force methods. So what we see, at least nicely come out of this, is the prefactor here is the volume element of the nd dimensional sphere, which makes sense because at 0 hyperradius, all you're doing is integrating over the hyperangles, so you should get the volume element of that. But let's move on. This is the trivial case. So if we add a second particle, we get this kind of nasty sum, but it turns out that this is just the confluent hypergeometric function. So again, that's already known. And let's keep going. So we add a third Jacobi vector, so 4 bodies. And now we have almost the 1f1 function. So this is where I got kind of frustrated when I was doing this method, because if this wasn't here, it would just be the 1f1. But it's basically weighted by some coefficient. But the coefficient is actually just a simple polynomial that truncates. And so we can actually do this numerically very nicely in a computer, because I can order my eigenvalues any way I want. So why not do them in decreasing order? So what you see is that every single subtraction here is positive definite. So the sum over all of these terms, I never have alternating signs. It's a positive definite sum. So very, very numerically stable and very fast. So as I'm sort of hinting at here, is this is always recursively defined. So this C of R of k plus 1 is defined in a similar manner, just following this pattern. So other things that are nice about this approach is that all of these weights here, that I call these weighting coefficients, they are independent of the hyperradius. So really the hyperradius only comes in this, what I call this almost 1f1 function, and this Gaussian prefactor. So yeah, I can't stress how nice this was to see and implement. And I think it was my math professor once told me that if you apply a trick over and over again, it's no longer a trick, it's a technique. So basically what I'm stressing is that this new technique that we've developed to do the matrix element calculations can translate anything that's done in the traditional method to the hyperspherical approach. So as I sort of stressed earlier, the hyperspherical explicitly correlated Gaussian method is now approximately on equal footing with the traditional approach. It's just that we still have this adiabatic parameter. And if you're interested, again, the review article that came out last year is very nice, and within it they also have a lot of references to matrix elements.
Excuse me.
Yeah.
By the adiabatic product, you are referring to
The hyperradius.
Okay.
Because we still have to solve everything as a function of this adiabatic parameter. So now that that excitement is over, I'm going to show what we've done to apply these new techniques to speed up some few-body calculations in regards to the Coulomb few-body systems. So just a bit of an experimental background and for motivation. polyelectronic complexes are kind of getting a revival. They were first, so positronium itself was first seen in 1951, and then about 30 years later, they observed the positronium negative ion, and almost again 30 years later, finally observed the positronium molecule, which is the analog of the H2 molecule, but for equal masses. Hopefully we don't have to wait another 30 years for the next experimental work. But what's nice about what they're doing here, they're basically producing a large number of positrons and then throwing them at porous silica. And what you end up with are long-lived positronium molecules, or sorry, positronium atoms, which then can interact with each other, and that's how they get the signature for the positronium molecules. But their motivation for us cold atom people is to actually get not so much a BEC of positronium, but actually get an annihilation laser. So that's their ultimate goal. Because you can think of, if you can make a BEC of positronium, it's nice, this nice coherent blob, then it starts to have annihilation, but because of the coherence, it has a cascade effect, and hopefully you can get a 511 keV annihilation laser out of it. Or at least
What's that good for? I mean, maybe I'm asking an obvious question, but why would I want to have that kind of laser?
To study systems at that resolution, I guess. I'm more interested in the BEC aspect. I think that would be pretty neat.
So what is the molecular plutonium? How many electrons? How many?
2 electrons, 2 positrons. So analogous to the H2 molecule, but with equal masses. So some background on these positronium systems. There's 2 types of positronium. There's orthopositronium and parapositronium, in which the total spin of the positronium atom is either in the triplet or singlet state. The triplet positronium, the orthopositronium, is the longer lived of the 2 at nanoseconds before it annihilates to an odd number of photons. And then we have the parapositronium, which annihilates to an even number of photons. Because at the positronium level there's 1 electron and 1 positron, it's also symmetric under charge conjugation. And so whenever you have an odd number of photons, that's the charge conjugation operator with -1 eigenvalue, and an even number of photons is +1. So some of the things they have to deal with in these systems is spin conversion, in which the 2 long-lived orthopositroniums would spin flip into the pair of versions with 2 times the energy difference of that spin flip. But the more interesting conversion problem is having some third particle interact with the 2 orthopositroniums to produce the positronium molecule. So that's what we're going to be looking at in our hyperspherical picture. But what I've shown on the right is also just a schematic diagram of the energy levels we can expect in the positronium system. So we already know that the even parity, 0 spatial angular momentum is what gives us our positronium dimer. And then we have the breakup threshold into 2 positronium atoms at, in these atomic units is at -1/2. But actually what Varga and collaborators have also seen is that there is a state with L = 1 orbital angular momentum. And it can be shown that this state actually can't decay. I mean, probably from a spin flip it'll eventually decay down. But in general, it should be a longer lived state with different angular momentum. And actually the experimentalists are trying to do spectroscopy now between these 2 states. So as I said, this is still ongoing research into these systems. So just a quick summary of some of the things that I've done using traditional correlated Gaussian is we can calculate the binding energies for many different electron-hole systems. And this is a chart that just summarizes those. I put this up because I will show some of these bound states in the forthcoming slides. But when sigma = 1, this is the equal mass system, and sigma = 0 is the hydrogen like system where you have an infinite positive mass, effective mass. But the idea is that when you go to lower dimensions, you have more binding energy. And I think that's all I'm going to pull from this slide, because I really want to show what I've done. So here's a first set of curves. These are the ground state adiabatic potential curves as a function of the hyperradius in atomic units, where this is the Bohr radius, in which I'm looking at one positron and two electrons, in which the identical positrons are in the spin, well, there's one positron, which is spin half, and the identical electrons are in the spin singlet configuration. So the lower curve here is for 2 dimensions, in which you see we do get a deeper binding energy than in the 3-dimensional case. And also you see that the generalized angular momentum barrier in this adiabatic representation you can pull in much tighter in the 2-dimensional system. I guess I should mention that in studying this, I used a 1/r potential for any dimensions, which might not be physically describing Coulomb systems as I go to higher dimensions. But at least in the 3-dimensional level, I can say that it does go to the positronium and electron breakup threshold. The limits as I go to large hyperradius are actually known from the work of Hirschbach, who looked at the dimensional scaling in hydrogen. And so just scaling his work to equal masses, I can also pull out the known asymptotes. So as the number of dimensions increases, and the potential isn't keeping up with the increase in the number of dimensions, what you see is the angular momentum barrier keeps increasing because I'm putting more and more kinetic energy into the system as I increase the number of dimensions. But this was for me just kind of a test that I could do things with my new code. But at least I can reproduce in a single channel approximation the 2 binding energies. I get a lower bound estimate, which is in the ballpark of what's already been done. So now looking at still the 3-body system, but I've changed the spin of the 2 electrons to the triplet configuration. What you see is that we no longer can get to the origin in which all the particles sit close together. And that can be understood just simply from the Pauli exclusion principle, because when the 2 electrons are in the triplet spin state, they spend more time farther apart. And so what you see is that the angular momentum barrier is already pushed out much further than if they're in the singlet configuration. The other thing that's kind of hard to see is the scale has changed dramatically in the ground state for 2 dimensions compared to the previous slide. I mean, that's a really small attractive dip there. It's in no way can support a bound state. So let's keep going. I have this new technique. Let's try and break it. So let's go to 4 bodies. So what we see here is the ground state for the 4-body system, 2 positrons, 2 electrons. And so the blue dotted curve here is when the identical particles are both in the triplet configuration. And the red dashed curve is when the identical particles are in the singlet configuration. So the first thing that we see is that when the particles are in the singlet configuration, spatially they can be much closer together. So that leads to a significant dip in the potential curve. And that dip can support a shallow bound state of the positronium dimer. So that was very nice to see come out. Whereas if they're in the triplet configuration, we don't have a bound state, and that's the configuration that would basically lead to the BEC. Because if you have the spin polarized positronium dimers, they don't form, a spin polarized positroniums, they can't recombine to form the dimers, so you just have a spin polarized BEC of positronium. The inset here is where I have the mixed spins going on, where I have a singlet and triplet configuration. And in this case, the breakup into 2 ground state positronium atoms is not allowed. I have to break up into a ground state plus a first excited state positronium. And I wanted to break my code even further, but it hasn't happened yet. So here's the 5-body system, which I have 2 positrons and 3 electrons. So I have 4 curves here, depending on the different spin configurations. So in purple, I have the singlet spin for the positrons and the quartet spin state, so the more symmetric spin state for the electrons. And the green curve is the triplet quartet, and then I have singlet doublet and triplet doublet. So what I see happening is there's a splitting between the two systems where the two symmetric states for the electrons really push the system into a more repulsive state. And I can think of that really as just all of the electrons spatially have to be much more farther apart because of their spin configuration. But I can confirm that they do break up in the large hyperradial limit to 2 positronium atoms and lone electron. In the other case, which is more interesting because it's still not confirmed, there's still a little bit of debate whether a 5-body bound state can exist in the system. And I see that when I have the electrons spatially more closer together, I have these 2 curves that go to the lower breakup channels of a positronium ion and a positronium, or the positronium molecule and a free electron. So in our single channel approximation, we actually did find that there was a bound state that can be supported in this red potential, but it actually lies in the continuum of the singlet doublet configuration, so it's most likely not a true bound state. But yeah, it was interesting. So these are all the ground states, but in continuing with looking at where my code finally breaks down, let's look at some excited states of the 4-body system. So what I have shown here are the excited states of the 4-body system, so 2 positrons, 2 electrons, in the singlet-singlet configuration. And because I have an even number of electrons and positrons, all of my states are also eigenstates of the charge conjugation operator. So let's do that to reduce our Hilbert space. And so I've labeled the curves based on, actually I should say, I'm plotting this up to the dissociation limit of a single positronium atom. So minus 1/4. And what I'm not showing is the ground state, which is this S that drops down to minus 1/2. So I label these basically by the excitation of the, so one positronium atom's in its ground state, one is in its excited state. So this is the first excited state, and then we have the second excited state, in which you can have either an S or D wave positronium, and then things start to get kind of not converged. Because this is a basis set expansion approach, so in the variational framework, if I don't include enough basis functions, I'll eventually not reach convergence as I go up in energy.
How many basis functions are you using here?
Here is only about 200 or 300, so not so bad. The 5-body system, just for the ground state, I was using of the order of 600. So to get even a few excited states of the 4-body system, I'm pretty happy with this.
So you having 200 or 300 states or basis functions for each state, or for the entire set?
This is all from one basis set, all of these curves. I haven't tried to individually optimize any particular symmetry. What I have shown in the thin red lines are the analytically known asymptotics. So that gave me an idea of how convergent I am. On the scale, it actually looks pretty good, but if I were to zoom in here, everything starts to get worse as I go to large hyperradius. So in practice, what we do is we tie on to the known asymptotes as we try and do scattering calculations. The thing I haven't mentioned is that we have this nice, clearly present ion curve that cuts through everything. So that's pretty neat to see, because in other techniques that I don't remember which one exactly, usually the ion channel has to be dealt with separately. But in the hyperspherical picture, we can do everything on the same equal footing. So yeah, that's pretty neat. And now let's change the charge conjugation. So back and forth. So what you see is that I change to the other charge configuration, I get the other set of excited states. So there's no state with this symmetry that goes to the minus a half. Instead, I have the p wave, the ion channel, and the p wave, and I should have F and so on as I go to more and more excited states. I think I forgot to mention the green lines. These are the energy levels of the sum of the two positronium atoms. And the black dashed line, this is actually the ion breakup threshold, where we go to the PS minus plus a free positron. So one of the nice things that we might be able to pull out of this is basically Landau-Zener transitions in which we can look at ion pair formation, because this ion channel will continue to go up to the black dashed line as we increase the hyperradius, and it's going to cross a number of other curves. But one of the neat things to see, if you remember that the -1 charge conjugation symmetry is the one that decays to an odd number of photons. And so what you see is that in just changing the charge conjugation, it doesn't produce as deep of a state, because you can sort of trace this ion channel all the way through as a 1 over R form, roughly speaking. And so it shows some evidence as to why, at least in this picture, the -1 charge conjugation symmetry just leads to less binding and thus longer lifetimes. So now looking at a different spin configuration. So now this is the triplet spin configuration with +1 charge conjugation. This is the system that would be more useful for the experimentalists, at least if they're trying to go for a BEC. Because the first thing you might dramatically see is there's no ion channel anymore. It's disappeared. So we still have the ground state, which we saw previously, going down to -0.5. But then we have some very shallow states that do give some phase accumulation, but in general don't lead to any binding.
Can you, I mean, you said that this would be useful information for making a BEC. Can you elaborate on what information from these graphs would be useful to
So
the experimentalists?
when we do the scattering calculations, which are still ongoing, we should be able to get inelastic scattering cross sections and other scattering properties from this approach.
For which channel or which?
Well, for all the graphs that I've shown, all the symmetries that I've presented so far, we could calculate the different scattering properties, which in general would be all useful for experimentalists, like the ion pair formation would be interesting to calculate. But if we wanted to go to higher scattering energies, especially for the triplet configuration, which is the spin polarized positron system for the BEC, I think this and its other charge conjugation would be the more relevant, just to get scattering from that.
Do you have an idea more or less of the critical, what is the estimate for the critical temperature for BEC?
I don't know the critical temperature offhand,
Something like a Kelvin or so?
but from what I'm going to show, the elastic scattering's been calculated for the two systems, the two different spins configurations, and it's really, really small scattering length. And so the downside to that is the system probably wouldn't thermalize that quickly. So they're more trying to overcome that by just sheer numbers, just trying to create a large number to increase their density as high as possible.
Just curiosity, I think that each PS atom,
Mm-hmm.
the PS plus PS must have some sort of van der Waals interaction, right?
Mm-hmm.
Do you know how much is the van der Waals length associated to that?
Not off the top of my head, no.
Or let's see, the size of the PS state, the lower state, how much is it? A few more? Yeah, that's to be.
Yeah. I would estimate on that order, but I don't know exactly.
And the PS scattering, they have determined.
Oh yeah, that's the next slide.
I have a simple.
Yeah.
So I have
In this case, I'm actually minimizing the sum of the energies. So as I randomly search my variational parameter space, I basically say pick the state, or pick the suggested basis function that lowers, say, the first 5 energies together as a sum. So I'm not actually optimizing a single channel. I'm optimizing simultaneously a sum of channels, or the sum of their energy.
Summation of the lowest few.
Exactly. So in practice, I'll usually start by optimizing the ground state, and then optimizing the sum of the ground state's energy with the first excited state, and then so on and so forth. And depending on my choice of basis function, if I just have spherical Gaussians, I actually get all the S-wave states very nicely. But say, in this case, the D-wave state doesn't even appear, which was really surprising. So I have to use another basis function that is built to do D-wave in order to actually see at least the asymptotically correct D-wave functions, or the D-wave character.
Is that a good quantum number?
Yeah?
Well, then, if you don't have that in your basis, you shouldn't get it. So if you only have
Well,
states
okay.
with S-wave character in
Maybe
your
it's-
basis, then you, right, I mean, if it's orthogonal, then we shouldn't be getting D-wave states.
Asymptotically, it's good, but not in the inner region. So if I tried to optimize just S-wave spherical Gaussians, I would actually get all the S-wave asymptotes spot on, but none of the D-wave or higher order asymptotes. But in the inner region, when I start to optimize there, then even with spherical Gaussians, I can get some D-wave looking potential curves. So.
So if I try to minimize one of the states, let's say the
Mhm.
first excited states, and basically do that for each excited states, do you get roughly the same answer? Or what's the difference?
No, I get the same answer.
Okay.
I mean,
It's just numerically heavier.
well, yeah, if I was interested in optimizing a particular state, I would focus on that. But in my interest was really trying to get the best picture possible of all states. And having everything in a single basis is easier to handle than having individually optimized potential curves, each of them represented in a different basis set. So I sort of mentioned that we've also been moving on to doing scattering calculations. Now this is preliminary data, but what I have plotted is the triplet configuration on the left and the singlet configuration on the right, where n equals the number of channels I've included from the ground state upwards. So as in a variational approach where we've truncated the number of channels, you see that we have to converge as we increase the number of channels. But what's nice is we're in the ballpark, so that was very encouraging. Other calculations put the triplet elastic scattering length at about 3, and the singlet scattering length at about 8.3 or so. So I'm showing that here using the traditional correlated Gaussian. They've calculated the elastic scattering lengths. But what's nice about this is we're in the ballpark, and even though we see some errors and we go to really, really low scattering energy, we understand those errors. We know why they're there. It's because we tie on to the known asymptotes, and there's kinks in our potentials when we do that. So, but we know how to correct it, and hopefully this will improve when we do that. We know it will. But the idea is this is just a test that we can do our normal approach of scattering using the R matrix propagation method, and that we can confirm already known results. But we want to move on to inelastic and other processes.
But how do you know where sort of your errors start to dominate? I mean, why do you fit those particular points?
If I were to plot, at least in a single channel picture, what the curves look like, I have something like this. And the energy levels here, the range, is very similar to the energies that I'm scattering at. So if I come in at a scattering energy like this, it becomes very sensitive to the form of the potential underneath. And because we're connecting to the known asymptotes, I get this kind of weird discontinuities, or even something worse if I don't have converged curves. And as I go to lower scattering energy, I get more and more sensitive to the behavior of the potentials. So that's why I'm actually doing these linear fits to higher energy. But in general, all of that should change at least a little bit when I fix this issue. I just didn't have time to do that. So this is all very exciting for us, because now that we have a method that's very fast and more or less free of errors, we can think about other problems that we might tackle in the future. So for the systems that we're currently studying, we would want to do more thorough investigations of the scattering properties. And as I mentioned earlier, the ion channel shows up on equal footing with the rest of the other dissociation processes. And because of the crossing of the ion channel with all of the other atom channels, we can hopefully get ion pair formation rates. And also, I didn't mention, but everywhere in my code, the mass is actually a tunable parameter. I just chose to do everything here at equal mass. But it's interesting that we might be able to learn something about how the equal mass system evolves to the hydrogen molecule just by tuning the masses. So that could be pretty neat investigations. And lastly, because as I mentioned, everything seems to be analytical in 2 dimensions, very nicely analytical, just maybe we could look at some Hall physics or other things that are known to be of interest in 2 dimensions, or even the newly reported dropletons, which are 8 or more, so 4 pairs of holes and electrons that appear in 2D that are themselves bound states. So, but yeah, thank you for your attention.
Yeah, thank you. We have time for questions. Yes?
So this, your new matrix element calculation, is this only for total angular momentum 0? Is
Nope.
It, so you can still extend to higher angular momentum?
Yeah, I've already done that. I actually didn't show. I had a preliminary curve for the L equals 1 bound state for the 4-body system, but it looked too ugly for me to present it to all of you.
Okay.
Yeah, it's not that. Of course, when you do this, the basis functions do get more complicated, but the bottom line is you can always translate what's already been done into this approach.
Well, I mean, I guess what you've done here, uses these explicitly correlated Gaussians, but then going to the higher angular momentum required this stuff that you had worked on with.
I used the global vector approach.
Yeah, that. Because like when Javier was working on this, I remember he had to do this, like, if you wanted to do a P wave, you had to put in a fictitious n plus first particle which was pretty horrific.
Don't have to do any of that. I can avoid that. But you do have to do coupling to harmonic polynomials to get your higher angular momentum states.
But I mean, do the expansions to this matrix element method still come out as simple to evaluate?
Yeah.
Or is it, okay, it's still some geometric, hypergeometric series or pseudo-hypergeometric?
So the only difference between just doing the overlap versus doing, say, like the kinetic energy or other things is instead of just having factors of d over 2, keep going back. These become different, but that's about it. Besides, you get some additional coefficients, and the powers of these terms are different than just d over 2. They might be d over 2 plus 1, but that's it. I mean, it's a very easy generalization to other things.
So it looks like the Gaussian works also with Coulomb interactions.
Mm-hmm.
And are these matrix elements analytical too?
Yes. So that's actually an interesting question. I didn't put the Coulomb or power law in general interactions up, but what ends up happening is you get additional term that looks something like, so you get this base form plus something that looks like this. It's a sum over j equals 1 to n. So you get this product as well as this base form here. But what's interesting is this itself, you can just do a complex root finding, because this turns out to be just a product of these to the order, yeah, this is all raised to the, where k is the order of your power law potential. So you basically just get additional factors that look like what's already been done, depending on your power law. So
a potential like Lerner-Jones,
I think could be possible, yeah. So it does involve an auxiliary step of solving for the roots of a polynomial, but in general, the power law potential is no more complicated.
And what if I have a completely numerical interaction? Like, let's say I want to treat the rubidium with the positronium.
Well, then you would probably want to just solve the 1D numerical integration as efficiently as you could.
That would rely on 1D multiple.
Yes. So yeah, at the worst, you've reduced it to a 1D numerical integration. At best, everything can be done analytically. But the downside of using the Fourier transform, it's a very oscillatory integral. So I originally did all of this just numerically, and before I did everything analytically, and I found I did run into some problems of trying to get high accuracy.
So yeah, so what would be your main source of inaccuracy? From your base?
The number of basis functions,
Number
yeah,
of basis
at this
functions,
point.
is it?
The linear dependence is pretty, yeah, this is a non-orthogonal basis set. I guess I glossed over that, but you could have seen that because the overlap integrals gave us non-zero numbers. But you still have to worry about linear dependence, more so at small hyperradius than large, but really sort of everywhere. But that's usually pretty easy to avoid. Yeah?
Cool, in 2 dimensions with your lock.
Mm-hmm. Yes?
Does that complicate your method?
I haven't explored it yet. I do know of that issue. But still, you can reduce it to a one-dimensional numerical integration, a numerical Fourier transform, even with the log.
But it depends on which world you're living in then.
Okay.
Because it's still 1 over r, if you confine, if you're Hall physics, for instance, it's still 1 over r. So, I mean, it's true, if
Yeah.
we live in a 2-dimensional world, but I don't think we do.
Right.
So in that sense- No.
Well, I'm puzzled by your statement you haven't investigated that because you showed us 2D curves. So you,
But I kept the 1 over r. Regardless of the number of dimensions, I kept the 1 over r fixed. So I didn't change the interaction potential with the number of dimensions.
How would you confine the electrons and positrons in 2 dimensions?
Well, one of the things I could do is put another Gaussian in the 3rd dimension, but just try and make it tight.
What's the physical? What physical method do you use to confine the electrons and positrons very tightly?
Well, in my code, I could directly work in 2D.
How would an
In practice, experimentalist. Ah, I see, I see.
An optical lattice, for instance.
Yeah.
so you're asking how do you maintain 1 over r in 2D? I think the answer is you can't to do a different calculation.
My question is maybe it's not a theoretical. How to do this 2-dimensional system, to realize this 2-dimensional system. Yeah, like a graphene, but in terms of graphene.
You really use a super strong magnetic field so that everything combines in the lowest level level. Roughly.
But you need the confinement length to be shorter than the bore radius. In order for the system to be.
What that means super strong.
Question about this your calculation. So
Mhm.
you can calculate the binding energy of the positronium molecule.
Yeah.
And I wonder if you can also calculate its lifetime.
Everything I've done is non-relativistic. I'm sure I could estimate it.
Is that given by the probability that the electron and the positron are close together?
Yes.
Mhm.
It's given by that, you can evaluate that probability. you can write that like that.
I personally haven't looked into it in much detail yet.
It's a
but-
famous formula by Jackson.
Okay.
That people would want to have to use to determine the lifetime. It's just you have to do. I think that I remember looking into that a long time ago, and basically yes, it's related with the probability of having two electron and proton to be on top of each other plus some funky stuff.
Always the funky stuff.
There are other questions? Sheena?
Yeah, so there are theoretically about the bound state between electron or positron and the muon?
Yes, so they, my recollection of some of the literature that I've read, they look at other complexes with positrons, and actually positron studies. I'm sure there's even a review of it by now, but I can't pinpoint exactly what you're asking for, if that study in particular has been done.
For example, what about this muon electron or muon positron atom? And then you could also consider the molecule formed by these atoms.
Oh yeah. Muonium, yeah.
Yeah. Other questions?